I'm Tom Roby from the University of Connecticut, and I'd like to tell you today about the 11 clocks problem. Since this is only my second time at G4G, I thought it might be worth telling you a little bit about who I am. Mathematician and educator, interested in combinatorics. I've worked a lot with K-12 teachers, high-ability high school students at various programs. And I have particular interest in folk dancing, Japanese culture, and linguistics. And there's a picture from me yesterday doing an East Macedonian line dance with somebody in a Japanese setting, which got to combine a lot of my favorite things. As far as Bulgarian singing goes, we won't quite get there, but Bulgarian solitaire will make an appearance. So this is all joint work with Jim Prop, as you may have seen if you carefully read the slide I flashed at the beginning. So imagine you have 11 clocks, each showing the time in a particular city. And on the hour, you compute the median value of the list. So this is not Greenwich Mean Time, this is Greenwich Median Time or something. And you repeat this 11 more times at 1 hour intervals. What is the mean of the medians? Okay, so you may not be clear to you whether you even have enough information to solve this problem in general. And just in case you're not sure what it means, let me just do it. If I take this completely random sequence, 3, 1, 4, 11, 5, 9, 2, 6, 5, 3, 5 of times, and then you see how there, as I go down the columns, I'm just incrementing each time by 1. And it's a little hard to look at the data that way, so it's better if you, as always when you're looking with medians, if you order the things in increasing terms. But then it's better for this problem if you keep the clocks in each column constant. So if you do it that way, then you end up with things that are at least increasing on the cylinder, and you can compute the median in red there for you, and you can quickly compute that their mean is 6.5. Which, if you went to Alex Bellos' talk, you know is just as good as 11, right? I mean, if that's your favorite number, you can make 11 out of lots of ways. So there's some natural questions here. You know, what's special about 6.5 besides the fact that it's as good as 11? And is that always the answer? And I already mentioned that it may not appear like you have enough information to answer this, but in fact, I gave you more than enough information, more than you needed. Some of you may be able to guess the answer, but the point is not just that, but to see if you can come up with a nice way of explaining why the answer is true. And most of you probably realize that if we were talking about the mean of means, that would, be too easy as well as too mean. A mean of means sounds like you're talking about income distributions or something where you'd want medians anyway. A mean of means would be a very well-to-do mean. So here's a variation. What if some of the clocks are broken and run a bit faster or slower? Will that affect things? Or you could think of it in terms of like the talk we saw earlier about standardization of units. So if some clocks are running on British imperial seconds and other are running on metric seconds, right? Then you might have variations in different cities. So we still don't fully understand this problem, and people who have ideas about this are welcome to talk to Jim and me. Bulgarian solitaire, as many of you know, is a game popularized by Martin Gardner back in the early 80s. And it's a very simple dynamical system. It has nothing to do with cards or the values on the cards. It's just these chips. You start with a bunch of heaps of cards. You remove one from each heap and use those to make a new heap. And you just keep doing this. So here's a quick example. I'm going to reorder things. 0 heaps get ignored, and I'm going to reorder things so they're decreasing in size. So for n equals 8, we get a couple of different trajectories. You've got the 5, 3. You take one card off of each of those. That leaves you with heaps of size 4 and 2 and a new heap of size 2, which I've underlined. Okay? And then you take one card off of each of the 4, 2, 2. That leaves you with 3, 1, 1 and a new 3, which I've put at the beginning so I can keep them in decreasing order. And if you do this, because there are only finitely many possibilities, eventually you'll get into a cycle. You might have some sort of a tail, but eventually you'll get into a cycle. So here we are again. And what's interesting for the kind of work that Jim and I do is that the mean number of heaps in each cycle will be the same from any starting point. So just in the 2 examples there, you've got 7 heaps between the bold-faced ones in the cycle, 3, 3, 1, 1, 4, 2, 2. And then on the one below that, you'll also see that you've got 14 over 4, or 3.5 heaps on average. So it's a different invariant. And this is very different from the kind of thing that appeared in the Gardner original article, where if you start with a triangular number, you end up in a cycle that's exactly one fixed point. So that was maybe more enchanting. So here's the general thing we're doing. we're looking, often when you're dealing with kinds of puzzles, you're looking at various configurations, you're interested in what doesn't change, what's invariant, or what's something that helps you keep track of things as you go along. And so we're interested not in something that's invariant as you move from thing to thing, but once you're in some kind of an orbit where you cycle back around to the beginning, we want those averages to be the same no matter where you start. And so this is a phenomenon that we call homomessy, and there's a math research articles about it. And then here's some, just quickly I'll flash you these applets that were written by PostScript hacking by Mike LaCroix that show this phenomenon happening in some gridded posets. And if you look at the area underneath all of those zigzag up and down paths, well, see, there's only one orbit, so that's not exciting. So I have to show you one more, and then I'm probably way out of time. But here's the other orbit. So what's happening is you're just shifting the down-up cycle cyclically each time. I don't really have time to fully explain it, but if you're interested in this, I can show you more and even more applets like this. You can only run these in Adobe Acrobat, by the way, because they take advantage of a bug in Adobe Acrobat. So you can't do this in preview or something. You actually have to. And the PostScript does all the computations. All you do is input the paths as downs and ups, and everything else gets computed and done on the fly. So for more information, there'll be the gift exchange booklet will have something that talks a little bit more expansively about this, gives you the solution to the problem if you want to look at it. Don't look at it if you don't want to. There's more stuff you can get by Googling me. And please let us know if you encounter this phenomenon in your own work in puzzles. We think it's lurking out there in lots of different situations, and recreational math and puzzles is one place where you might find it. So thank you very much.